Hello, everyone, and thank you for joining this week's Landscapes Live seminar series. And my name is Vivi Petersen, and I'm chairing the session today. And then we also have Philip Steer and Charlie Sobi that will be moderating the chat and the questions. And we're very happy with so many participants again this week. We're still letting people in. And this will be the final talk of this winter series, but we will return already from the 6th of May with a spring seminar series. So please look out for the program and we'll announce it as soon as possible. And today we're lucky to have Simon Mott giving a talk from University of Edinburgh, and the very interesting title is "If you don't like the stream power law, wait until you get a load of what we do on hill slopes." And yeah, I'm really looking forward to this, and so are everybody else, Simon. So I hope you're ready to start in a minute. I just want to say that after the talk, we'll turn on the chat, and you're welcome to ask questions and add comments in the chat. And you can also raise your hand, and then we can turn on your microphone and you can ask a question directly. Yeah.
Okay.
So with that, I'll give the word to you, Simon.
Okay, thanks, Vivi. Yeah, you're excited about the talk because you maybe haven't seen it yet. Just a kind of precursor, pre-information. I've got my laptop on my cat tower. Maybe you can see it's on a cat tower. So, and the cord's not quite long enough. So if the laptop crashes off during this talk and I just go blank, we agreed that Vivi had a comedy routine, some really top-notch Danish comedy that's gonna come in if my laptop falls off. So that's about to, you know, I'm kind of looking forward to my laptop crashing off. Okay, yeah, I'm going to
it will be in
share
Danish,
my screen.
right? So
yeah. Well, Danish humor is the best humor. Okay, let's share my screen. Start the show and turn on subtitles. Okay, hopefully people can see this and see me. First of all, I'd like to thank the Landscapes Live team. It's just been such a great seminar series. There's been so many good talks. I'm a little bit nervous about living up to the standard so far, and also I sort of, it's getting near the end of term for us. I've actually got a virtual field trip to do next week. I'm getting quite tired. I don't know about you, but I just thought I would put in a kind of fun title and abstract. And it seems to have sort of built up a little bit of pressure here, high expectations. I just don't want you to get your hopes up. If you're expecting humor, the humor will be all kind of font based. So there'll be different fonts that might be funny to you. I got an email about the talk from Keith Bevan. Keith Bevan emailed me saying, "Oh, I like your abstract." And it's kind of like, oh, well, I'm not quite sure how you could get more pressure heaped on to the talk. You've got emails from Keith Bevan. But anyway, I also was wondering why I was invited to give this talk, to be honest, because two of the members of the organizing committee were former PhD students at Edinburgh, Rebecca and Boris. There's a picture of Boris here, and they know my talks are kind of boring. So I was wondering why I got the invitation, and I think probably because I've got two papers in press with Boris, and he probably wanted me to, well, in review or in revision, and wanted me to talk about it. So I'm just going to show these two papers. You can go onto the open access and look at Boris's really cool papers, and I'm not going to talk about them again. I just want to give a little thanks. I'm not sure if the people I'm about to mention are here, but we had a editorial review that was super thorough, really improved the paper. So thanks to Liren for that. And then I also want to give a shout out to Adam Forte, who didn't destroy our paper despite the fact that we misspelled the name of his favorite mountain range. So don't make that mistake. Okay, what is this talk about? I had my silly title. I had a kind of grand plan. I wanted to give a kind of overview of where I've come in my thinking about hill slopes, and then talk about the amazing papers that have been coming out recently from a bunch of other groups. So you know, go through the new results in hill slope geomorphology. I don't really have enough time to do all the things that I wanted to do. So what you're going to get is about 2/3 of the talk looking at some of the things that we've done over the past few years. A little bit of me was involved, and a lot of these collaborators. I've been really lucky to have a bunch of great collaborators. Much of what I'm going to show is work that Martin and Stuart led. And then the last third of the talk, I'm going to highlight a few new developments that I think are really interesting, and give a little pause to what we've been doing. So, you know, a little bit of introspection about our approach. I think hill slope geomorphology has come a long way in the last 25 years. It's made huge bounds in 25 years. And you might sort of think, well, 25 years is kind of a long time. Why aren't you going faster? But if you scale for the amount of investment in long-term hill slope geomorphology, 25 years in hill slope geomorphology is like, you know, 1 month in other fields. So I think we've come quite far, and I want to show you some of that progress. So I want to set a little bit of context. What are we actually kind of looking at in landscapes, and where did we start? So humans have made this kind of basic observation probably for tens of thousands of years, but G.K. Gilbert wrote it down in this paper in 1909, and there was a very basic observation, which is hilltops tend to be convex in unconsolidated materials, and stream beds are concave upwards. And I kind of think it's such a fundamental observation of many landscapes, maybe even most landscapes. I feel like if you're teaching geomorphology, at the end of the course, your students should be able to have some kind of rational answer if you ask them, why are hilltops convex and channels concave? So there were a lot of kind of, yeah.
Can I just interrupt you for a second? There is a gray bar over your screen. Okay, now it actually disappeared.
Oh, you know what? That's
okay.
Those are people waiting to be admitted.
Oops. Ah, okay. So it's something I can fix, actually. Okay. Great. I'll do it.
Right.
Continue, please.
Okay. So there was some qualitative observations about that, you know, in the early 1900s, late 1800s. But we wanted to get some kind of quantitative way to explain why hilltops are convex. I've lost control. And so what happened in 1960 was that W.H. Culling wrote this paper, which really brought geomorphology sort of into the 17th century. And I say 17th century because he's introduced mass conservation, which of course has been around in lots of other fields for a long time, and a flux law. So those two things combined are everything you need for a landscape evolution model. So what might you do with a landscape evolution model? Why might you actually try to understand why might you have a flux law? Why might you try and understand what the landscape's doing? Well, you might want to know, for example, if you've just got topography, how fast is the landscape eroding? You might want to know something about the history of the landscape, how it might have changed through time. You might want to know something about what might happen to the landscape in the future. And to make any of those predictions or reconstructions, you need some rule about how the landscape's going to respond to changes. So what you need is something in a paper I'm about to show called a geomorphic transport law. And I'm gonna read this. So this is a paper which was very influential. You know, I think that if you're doing long-term landscape evolution, you probably ought to read this paper every couple of years and think about, well, am I, you know, upholding I think that this has driven a lot of philosophy of what we're trying to do by a lot of people in geomorphology. So what is a geomorphic transport law? It's a mathematical statement derived from physical principle or mechanism, which expresses mass flux or erosion caused by processes that can be parameterized from field measurements, tested in physical models, and applied over geomorphically significant spatial and temporal scales. So this is actually a very high bar. And I think of what my group's been doing. Are we hitting this bar? I'm not sure if we're hitting this bar. What we are doing is trying to test some of the models that might have gone into physical models. But this is a high bar because we have a big problem in geomorphology, which is, so if you have a physical model, real landscapes are made of very heterogeneous granular material, and they operate on a long time scale. So getting that into a physical model is really tough. So you need to speed things up in your physical model. If you do something that's very intensive with the actual physics of the granular interactions, it's going to be pretty tough to do this second thing. So we have this kind of compromise. We have a kind of reduced complexity, but sort of physics-based model. That's the ideal. And then when I read this last line in the abstract, I sometimes get a little bit depressed because it's talking about, well, the rule-based approach, which is presumably not what you want to be doing, can only be tested with the rules-based approach can't be tested directly. They can only have model comparisons. So do models match an expected or observed state? But when I get depressed, I just go to the conclusions of this paper, and they are inferring that with high resolution topography, you could sort of run pseudo experiments. So you use the real topography and you test it against your proposed laws and see how well the different metrics line up in your real topography. So I like to think this justifies what I'm doing. Maybe the authors of this paper disagree. Okay, so what was Culling's transport law? It was very simply, sediment flux is linearly proportional to slope. So there's a little picture of it. What are the advantages of this flux law? Well, one, it is exactly analogous to chemical and thermal diffusion. And lots of clever people in the 1800s worked out all the solutions to this. So you have transient solutions, you've got all sorts of two-dimensional solutions, you've got millions of solutions to this, from which you can pick and choose, and you can seem super clever because because Fourier figured out all the maths, and then you put it in your own paper and you bask in the afterglow. Another thing that you can do with this model is that it's very easy to implement in numerical models. It's linear, it's easy. The big disadvantage of this is that it's wrong, and it's more wrong than the alternatives. I'm going to spend a bit of time talking about how it's wrong and comparing it to some other flux laws. And you might think, well, that's kind of a bit of a straw man because no one uses the linear flux law. But there are still some numerical models that use it. I'll talk a little bit about that in a few minutes. This was the justification for the linear transport law. So was there a physical experiment? Was there any mechanistic understanding of what was going on in the soil? The answer is no. It was. This is the full justification for using this theory. Okay, so how would you actually test it? We're going to test it, or other people have tested it, against topography. And the first class of tests are these steady state tests. So what we do, we assume uplift and erosion are balanced. That simplifies the equation. You don't have any time differentials in your equation. You then plug your flux law into the conservation of mass equation. That produces a topographic result, which you can compare to real landscapes. You can do that in one dimension, or you can do it in two dimensions. So here's an example of solving the linear flux law for a couple of different uplift rates and a couple of different parameters. Okay, so what does the linear flux law do that is not in real slopes. So one thing that it does, this is images from a paper by Josh Roaring and colleagues from '99. This is an amazing paper. I think, you know, this is one of these gold standard papers that everyone should aspire to write papers like this. But first of all, what they were doing, they were comparing the predictions of the linear model against real topography. The top panel there is the elevation as you move away from the drainage divide. And so if you're in the linear model and you are standing on the surface of the hill slope and you walk away from the divide, it just gets steeper and steeper and steeper and steeper and steeper. Okay, that's that dark black line. And the lower panel is the gradient. It's getting steeper and steeper and steeper and steeper as you go away from the divide. Real landscapes don't do that. As you go away from the divide, they start to get steeper, and then the gradient evens out. So it turns planar as you go away from the divide. And we see that in lots and lots of landscapes. And I'll show you some images of that later. So, so the linear law is not doing what real landscapes are doing. Secondly, here's another paper by Josh that was really excellent. In this one, he took a small basin or a series of basins in the Oregon Coast Range where we think we can make this steady state assumption. And he compared real topography with the outcome of that linear flux model. And what you see is the qualitatively, the linear flux model is not doing a very good job of reproducing the surface topography. Okay, so you've got two steep side slopes. So if you look at the gradient images on the right, they're too red compared to the real landscape, and the divide is too wide. So it's not doing a very good job. Yeah, and so I should say, so this isn't doing a good job, but people still use it in numerical models. I don't want to kind of name and shame anyone. And I actually think in some cases, it's okay. Because say if you're trying to model a mountain range, usually what happens if you have a coarse grid scale, you're just modeling fluvial incision, you end up with way too much relief if you get the channels all the way up to the divides. So usually what people do is they just, because that looks offensive, the relief is too high, they might put a little diffusion thing on the top to really just give the landscape a haircut. So I think this linear model, if you're using it in big numerical models of mountain building, you really ought to call this kind of the haircut model. And if you say that in an EGU talk, I'll buy you a drink of your choice if you call it the haircut model. And in a paper, I'll buy you a dinner. So please call it the haircut model from now on. Okay, so with all these flaws, there's an alternative transport laws were proposed. So these two papers kind of independently derived what was essentially the same equation. So the top paper used a kind of derivation of ballistic particles projected along a hill slope. The second paper, which I mentioned before, had a kind of combination of friction, disturbance, and gravity. There was also a physical model associated with that. And they ended up with this flux law. This has been called lots of different things through the years. If we're just being very basic, we can call it the nonlinear model. You'll hear me calling it the nonlinear model sometimes. I might sometimes say the local nonlinear model as well. So please be aware that we haven't as a field really settled on the name of this law, despite the fact that I'm going to show you it does pretty well in lots and lots of different contexts. So this is back to that Roaring paper in 2008. Again, take a few small basins, have it uplifting at the rate that they think is happening, and compare the model output to real topography. And what you find is this flux law can reproduce a bunch of features that you see in real topography. So it gets the angle of the slopes around right, the narrowness of the ridge is reproduced, but then you also produce a lot of subsidiary data. So here you've got curvature versus gradient. The top panel is the real landscape. The bottom panel is the model. And you're able to capture a lot of the observed behavior. So far, so good. I will mention that a model very similar to the one I'm showing you here, the flux law in the top left, Josh also tried a depth-dependent version thereof, which did a little bit better. But I'm gonna, near the end of the talk, I'm gonna talk a bit about the depth dependence. Okay, so in this test, you're sort of getting something that looks fairly good. What I've done with my colleagues is test it over and over and over again. And you think maybe it's a bit repetitive, but I do feel we're, and as we'll get near the end of the talk, we're not totally sure how well these laws are doing. Again, it's not like we're not modeling subatomic particles where we're trying to get the exact right physics. Okay, we don't have all of the forces and all of the materials and all that stuff. It's a lumped kind of model. So we want to keep testing it. We want to keep pushing that model. At least that's the philosophy I've been going with, to try and build up more and more confidence that it's actually doing a good job. So that's what we tried to do. So a different test is, in that previous paper, there was a small basin. What if we wanted to look at loads and loads and loads of hill slopes? Well, what you can do is you can solve the equations, the conservation of mass plus the flux law, steady state, and predict the relief as a function of hill slope length. So you end up with a prediction that looks like this on the right-hand panel. The nonlinear flux model has a different relationship between relief and hill slope length than the linear model. So the advantage is using this method, you can measure a lot of hill slopes. The disadvantage is that the hilltop flow routing is a total headache. It seems like a trivial problem, but you've got to filter all the ridge tops. You've got to know where the channels are. You've got to try and get rid of depositional areas. You've got to worry about all kinds of nasty edge cases. You've got to filter out slopes where the profile curvature is too big, or sorry, the planform curvature is too big because you don't want a divergent hill slope. So it's very annoying and messy. And Stuart Grieve and Martin Hirsch spent a lot of time working on this code, and it nearly drove them insane. And in our code, we get messages like this. So I did promise some source code. It's not really code, it's a comment. But anyway, you've got some LSD topo tools. And if you want to go through the 100,000 lines of that code, you can find lots of wonderful Easter eggs like that. You can do that after the talk for the next 48 hours. Okay, so what does the data look like? So on the left here is that prediction. On the right is a bunch of landscapes where we measured loads and loads of hill slopes, and again, filtered to try and make sure we tossed out the ones we thought weren't going to behave properly, not really a one-dimensional approximation, that sort of thing. And we ended up with these data sets. And the results are that the relief structure is consistent with that nonlinear model. So that is a second independent test that tells us, well, the nonlinear model seems to be doing okay. But we're not done yet. We've got more tests. I need to go into some of the predictions of the model because the next tests are going to get a little bit more complicated, and you're going to need to follow along with me. So what are the predictions of the nonlinear model? One is that as you increase the uplift rate, and again, we're in this steady state world, so uplift is equaling erosion. The image at the top are predictions of hill slope profiles. We're using that nonlinear model. We're increasing the uplift rate. As you increase the uplift rate, the hill slope grows with more and more relief, but the problem is it's limited by those side slopes. So the side slopes eventually reach this critical slope angle, this S sub C parameter. They can't steepen beyond that angle. So if you just kept on getting more and more and more uplift, you just get longer and longer straight slopes, and you'd be left only with the top of the divide that would still had some curvature. And the prediction of the model is this. So on the left, or in the red, you've got the relief as a function of the uplift rate, and you could substitute erosion rate for that. In the green, you've got the hilltop curvature. So the relief peaks out, limited by those critical slopes, but the model predicts the ridgetop curvature does not. It carries on increasing, okay? That is actually the same prediction as the linear model. The reason why is that the nonlinear model looks a lot like the linear model at low slopes, and the divide in a one-dimensional hill slope by definition has 0 gradient, okay? So you end up with these two predictions. The relief is limited, but the curvature can keep increasing. Okay, and just to show that this isn't totally crazy when compared to real landscapes, this is some data, a kind of famous data set from Roman. Last week he showed quite a bit more nuance into data sets like this. But if you take erosion rates that you get from cosmogenics in lots of different basins that are steep, and you measure the average slope, you tend to max out at a particular kind of threshold slope. In this case, it's around 35 degrees. In this landscape, this is San Gabriel Mountains. There's a few other studies that do that have very similar results. So there was another study by Steve Binney and colleagues at around this time that shows the same thing. And then I'm going to show another paper later in this talk that shows effectively the same thing. So you get this limiting of the slope angle, which is related to the relief is related to the overall slope angle. So you get this limitation. So that checks out. The next one is the erosion versus curvature thing. Martin, during his PhD, tried to get this out of the Feather River in California. So we have a nicer looking figure in the JGR paper, but we've reprocessed some of this data that I'm working on a project with Manny. I'm going to show you some of that results, but this is the kind of reprocessed data where we've tried to make sure that we don't have basins on either side of the divides going at different rates. But the original Feather River data, it looks pretty much like this as well. And then if you do it in a lot of different places, and I should back up. So we're measuring the median curvature above a cosmogenic erosion rate sample. So the erosion rate is all from cosmogenics. So this is the Feather River. This is a site in the Idaho Plateau. This is a site in the San Gabriel Mountains that's a lot more noisy, but you still have sort of positive correlation between curvature and erosion rate. And this is in the Blue Ridge Mountains in Virginia. So, there's not a lot of these data sets, but the ones that we have seem to suggest that the curvature is increasing with the erosion rate. I'm going to come back to this. I'm not going to talk about the recent Ben Asher paper, but in that paper, they had a carbonate landscape where this doesn't work, and they had quite convincing arguments for why that was. There's also something quite weird about this data that I'm going to talk about at the end of this talk that Manny and I and others have been working on. And just what does that actually look like? Here's a hillshade of the Feather River. I mean, it's kind of like when you get up into what we presume and we know actually from cosmogenics is the more slowly eroding landscape. It looks like you've passed over the landscape with a low pass filter. So that's what that ridgetop curvature is doing. So if you go down where you think it's eroding quickly, and you can tell it's eroding quickly from the cosmogenics, you get these very sharp ridges, and it just looks like someone's smoothed out the landscape in the places where it's eroding slower. So it looks like this low pass filter. So that's those plots I saw previously. That's what you're really seeing. And this is another paper that recently came out of the group from Cologne. This is in the Atacama Desert. But again, we've got on the right catchment-wide erosion rates and versus hilltop curvature, and you're getting this increase in hilltop curvature versus erosion rate. And also on the left, you've got that sort of asymptoting of the slope as you increase the erosion rate. The axes are flipped on that panel C compared to Roman's paper, but it's showing the same thing. Okay, so we've now sort of thinking, well, these seem to be true in real landscapes, these two relationships between relief and curvature. Can we do anything with that? And one thing that we've argued is that because relief asymptotes, if you're going to extract erosion rates from a place where you don't actually have cosmogenics, the ridgetop curvatures are probably a good place to start and not the average slopes. So don't use average slopes to back out erosion rates. Okay, so one thing about this is if we want to compare relief and curvature, we can't just use the same relationship for every hill slope because longer hill slopes have more relief. So let's say we wanted to compare these two things, we need to normalize for length. We also would want to try and non-dimensionalize for other parts of those equations. So there's two parameters in that nonlinear model. There's a sediment transport coefficient, and there's that critical slope. So we normalize for those things, and we can end up with a relationship between the relief and the curvature. Another classic paper, Josh and colleagues, every few years puts out a kind of classic paper. So this is another one everyone should read. What are these normalized relief versus normalized curvature plots? So first of all, the normalized relief and curvature are the relief and the curvature of the ridge tops normalized by these hill slope length, by the sediment transport coefficient, and by the critical slope. But what you should really think of this is as a mashup between these two curves. So it's trying to get at the relief structure, but in the relief curve, in this one, you're looking at the relief as a function of the uplift rate. In a real landscape, or again, you can substitute that for erosion rate. So you don't know what the erosion rate is everywhere, but you can measure the curvature everywhere. So you're using the curvature as a proxy for the erosion rate and then comparing it to the relief. So that is where this curve comes from. It's like a mashup between the relief and the erosion rate data, but you've substituted curvature for erosion rate, okay? Hopefully you're all still with me. I have no idea. You've probably all gone off and taken your dog on a walk or something, but anyway, I'm gonna hope you understand this. In addition, in that paper, they took a couple of places where they thought they knew some erosion rates, and they thought it was steady state, and they could calculate all the other parameters to non-dimensionalize this stuff. And this is what they got, 2 points or 2 places where it fell on this steady state curve. So that was a pretty impressive result. I thought that paper was amazing. We thought, well, we might be able to get a wider range of curvature versus relief information. So Martin and a bunch of other people, including me, went back to this Feather River site, and we compared across a large range of basins what the curvature and relief relationships were. And the red data is what we found, and they seem to fall pretty well on that steady state curve. Now, you could ask about, well, isn't this landscape transient? We spent a lot of time talking about that. We think that the hill slopes in this place respond more quickly than the channels. But again, we have more tests of this. But we do think that this is, again, another line of evidence that suggests that nonlinear model is doing okay. Well, I basically just spent a bunch of time telling you how we kind of think this nonlinear model is doing okay. And you said in your abstract, or I said in my abstract, I like to talk to myself about myself in the second person, that my abstract said I didn't know anything. And actually, I feel like we kind of are doing okay with the nonlinear model, but there's lots of little things in the back of my mind that make me nervous about the nonlinear model. And I'm gonna, again, at the end of the talk preview, I'm going to tell you a bit about those warning labels that make me nervous. But just hold on a second, think about my cat for a little bit, maybe get your coffee. And then I'm going to tell you about the transient behavior of this nonlinear model. So again, this is getting a little bit more difficult to explain, but imagine if you've got some hill slopes, and each hill slope is bounded, or you've got all your hill slopes and they're bounded by a channel. So there's a channel at the bottom of your hill slope, and it's incising at some rate, okay? Then there's a change in the erosion rate in the channel. It starts to incise faster. And we've spent a lot of time looking at rivers in lots of places. The incision, once you start to incise a river somewhere, that incision wave propagates upstream. So incision signals tend to propagate upstream. What happens to the hill slopes? If you're near the top of this channel and you haven't had that incision wave pass underneath your river, the hill slope doesn't know anything about that incision wave. So you've got low relief, it's slowly eroding above the incision wave. The curvature is it's very smooth, and your hill slope is very happy. So that is on point A in this relief versus curvature plot in the upper left. Now the nick point moves through the channel and it moves up. And what happens? Well, the channel incises. So the hill slope gains relief, but it takes a while for that signal to get to the ridgetop. So there's a delay between the relief growing and the ridgetop responding. What does that look like in this relief versus curvature space? Well, so you start down at A, where you've got low curvature, or it's very smooth on the ridgetop, and you've got low relief. You then grow relief without affecting the curvature. So that's point B. It pops straight up. And then once the signal of incision moves up the hilltop to the ridge, it then scoots on over to point C. Okay, so that is the prediction. So we speculated about that in that Martin's first PhD paper, and we thought, well, where could we try and test this? Well, so first of all, we did some modeling of this. We tried to see what the hill slope would do, this nonlinear model, how it would respond to changes in uplift rate through time. And it did, you probably could have predicted that before you ran the model, but it does what we expected it to do, which is the relief responds first. So this is the lower left panel. You've got, in the top panel, you've got a time history of uplift that we forced through this model. In the bottom left panel, you've got the blue line is the slope, and it's moving along through time. So the slope responds earlier than the curvature, which is the green line. So the result in that dimensionless relief versus dimensionless, so in this case, we've called it dimensionless erosion rate, but you can think of that as dimensionless curvature. It pops up and then moves over to the right and then decays back down. So that was the theory. Where are we going to test this theory? Well, there was this paper by George Hilly, Ramon Aerosmith, where they spent a lot of time figuring out this kind of interesting and possibly best constrained local uplift field anywhere on Earth. And because in the bottom of that image at the top, you have the Pacific plate moving kind of to the left of your screen, it moves over or through this uplift field, and you get uplift and then it decays. So this landform. So this is called the Dragon's Back Pressure Ridge. It's along the San Andreas Fault in California. So we had discussions about this. Martin and I talked about it. Mikhail was probably there. We were all talking about this this feature, and then we all decided, well, Martin was going to go back and run the simulation. And he came back into my office with a piece of paper, and it was this. And I just, you're all doing science. It can be pretty annoying sometimes. You submit your paper, the reviewers are telling you change everything, and some of them say that you're an idiot and how stupid it all is, and it can get kind of demoralizing. I feel this way sometimes. Why do I keep doing it? Because every now and then you get a result like this. You know, Martin came into my office, showed me this, and we were the only people in the world who'd seen this, and it just behaved beautifully. So what's going on here? You've got the points colored by the time along this uplift field, basically after the initiation of this increased uplift, and then so it pops up, it moves to the right, and then it decays back down again. So the transient behavior in this relief versus curvature space was following the theory of the model. So we were pretty pleased with that. That was quite an exciting result. I think that's still probably the best result I've had in my career. And then just a few more slides about some other things that we can look at in these landscapes. This seems maybe kind of rudimentary, I don't know, but no one had tried it before. So there are lots of lines of evidence to suggest that steeper channels normalized by drainage area or discharge, if you want to use discharge, represent faster erosion rates. So there's lots of data sets that show this. And we've argued that sharper ridges indicate faster erosion rates. So you might think that steeper channels would then correspond to sharper ridges. Again, seems kind of like a trivial thing to look at, but getting that data is a bit of a pain. You've got to do all this hilltop flow routing. You've got to find all the hilltops. You've got to do all the extraction of the channels. You've got to link them up. You've got to do all this. There's a lot of code. There's a lot of code that went into getting this to work. But we did this. So again, Martin led this work, and we got this data set along the Bolinas Ridge that has a gradient in channel steepness. So what you have at the bottom is normalized channel steepness. So that's just the gradient of the channel normalized for the drainage area. And then the green dots are this normalized curvature, that E star metric. So they are correlated with increasing channel steepness. And actually the relief in this case is also pretty well correlated with the increasing channel steepness. So, you know, I think these things are lining up to say, well, the ridgetop curvature is a sort of, at least it's correlated with what's happening in the channels. And, you know, these relationships seem to be consistent through a number of different tests. Okay, so now is the part of the talk where I start to get suspicious about what we've done, and I'm going to show some other people's papers. So what are the warning labels on this flux law? First of all, there's no soil thickness in it. So, you know, you might think that thicker soil will transport faster, and people have observed this in various experiments and some other studies. So there's no soil thickness in this model. The reason why we don't use soil thickness is kind of, well, we can't go out digging thousands and thousands of soil pits. So it's a major limitation if you're just using topography. And you know, I take the criticism that, well, how can you know anything without digging 10 million soil pits? My riposte to that is that, well, we're still getting decent agreement between this non-soil thickness based model and topography. But I acknowledge that that's a kind of flimsy argument. Secondly, what is the critical slope? Yeah, we're going to see in a second. It's pretty dubious what's happening with the critical slope in this model. And then finally, you know, a bit like the you know, various empirical coefficients that we use in geomorphology. Okay, we've got a sediment transport coefficient, D. What's in D? All of geology and geography, climate, particle size, you know, the vegetation, the rock type, you know, it's all lumped into D. What is it? I mean, I think we would ideally want to separate out the components of that sediment transport coefficient. So, you know, you're already sort of nervous about this, despite the fact that it had lived up to the geomorphic transport law rules. It was an experiment, all these sorts of things. There's still things that make us nervous about, or make me nervous about it. So the slope angle, go back to this relief data that Stuart led. What we do is we fit the landscape to a critical slope, and the critical slopes we get are really super low. You know, the original paper that Josh wrote in '99 had a kind of critical slope of 1.25. Whenever we try and tune our models, when we're using lots of topographic data, we get a much lower critical slope value. And it's a little bit of a nonsense how we do it. Well, it's not totally nonsense, but you have to do a little bit of believing that there's some averaging going out on the landscape. I'll show you this in a second. But again, this critical slope value is quite low. It's supposed to be the angle beyond which sediment flux is infinite. So this is from the Bolinas paper. Martin spent a lot of time trying to constrain this critical slope, and we ended up coming upon a method where we were trying to get the critical slope so that it was, you would only get less than 5% of the hill slopes or the slope angles above that critical slope. But again, it doesn't feel comfortable, does it? You think, well, you know, if the model's saying that's infinite sediment flux and you've got slopes that are steeper than that, you start to get worried. So I'm worried, Martin's been worried, Stuart's been worried, we've all been worried about this. And we have many, many conversations during review with Josh about this. Another thing, this all geology and geography into one parameter. This is from that preprint I showed that Manny and others are working on, so I'm one of the co-authors on this. What did we do here? We took a bunch of basins that we had the erosion rate. We then used the curvature around those basins, around the ridges on those basins, to back calculate the sediment transport coefficient, and we also looked at the curvature. So these are the data that I showed in separate plots where you had this kind of increasing relationship between ridgetop curvature and erosion rate, at which we were arguing was a kind of linear relationship. So first of all, you think, well, is maybe it's a climate signal or something? So that there's been papers talking about a climate signal. We wanted to use the same method to extract the sediment transport coefficient across multiple landscapes. So you needed LiDAR, you needed an erosion rate, you needed all these, Manny checked to make sure that you didn't have different erosion rates on either side of the divide. And what you get when you plot, another thing, all of these points are in crystalline rock. What you get when you plot them up is that the curvature of the ridgetops goes as the square root of the erosion rate, and it's not related to climate. So we related it to climate. There's no correlation at all. So others have shown some correlation with climate, but I think I would argue this is the most consistent data set. We find no relationship with climate. This is now in its second stage of review. John Pelletier has argued with us a lot about why we see this pattern, but we're still not convinced why this is, and it's very troubling, to say the least. There's no prediction in the rules to say that erosion rate should go with the curvature, or the sediment transport coefficient should go as the erosion rate to the square root, or to the 1/2 power, consistently across 3 orders of magnitude of erosion rate. So we're very troubled by this. It's a suggestion we might have some of the wrong rules. Now, a bunch of other people have suggested other rules. So I'm going to talk about two kinds of new papers. One is a non-local formulation. So the nonlinear model I've been showing this whole time is a local constitutive equation, okay, a local flux law. But if you look at slopes, you know, sometimes bits of pebble go more than just to the next, like they go far down the hill slope, okay? So a number of people have noticed this. Well, you know, again, humans have probably noticed it for 30,000 years, but listed below are some of the first papers that really delved into it on hill slopes. I'm using a formulation that is in papers by Don et al. What this says, usually these non-local formulations have some kind of formulation a bit like this, where you have this E term is an entrainment term, and the R term represents a kind of convolution of travel distances. So you say, well, when you detach a particle, how far is it going to go? You might have a kind of probability distribution based on some you know, idea about laboratory experiments or something, some intuition. So those two things go into these nonlinear models. This is more, I think this is more physically satisfying than that nonlinear model. These terms mean something physically, but there's a lot of parameterization that's involved in this. So like the entrainment is a whole family of models, the transport distance, a whole family of models. There was this really cool paper that everyone should read in 2018, and the reference is there. So in this paper, the authors were trying to test the nonlinear, non-local, and so the nonlinear in this case is the one that I've been showing. The local linear is the culling one, and the non-local is a specific formulation of that non-local equation where you get an exponential probability of transport lengths. The end result is that, well, one, it's really the first place that I've seen that's really tried to tune one of these non-local, this version of non-local transport laws to real topography. So they were doing this on some moraines. And what you end up with is a pretty good fit to topography with the non-local term. But you also get a pretty good fit with the nonlinear term. So, you know, again, the nonlinear one is doing okay compared to the non-local one. It has more satisfying parameters, more satisfying parameterizations. It's linked to real physical behavior, but its topographic outcomes are kind of similar to the nonlinear one, which is a lot easier to implement. So these non-local transport rules, and there's been a few ones that like there's various non-local transport equations that are featured in LandLab that are a little bit easier to compute, but you know, the full non-local transport equations are very computationally complex. So it's very hard to get a landscape topography prediction from them. It's harder than the nonlinear model, but they're more conceptually satisfying. And right now, the outcomes are difficult to tell from the nonlinear local model. There's another paper by that same group of authors that I just showed, where they're using spectral information, and they seem to think that the spectral information in transient cases might be able to discriminate these two things. But I think a lot more work can be done there. So one of the disadvantages of this is much more computationally complex. I just want to highlight, so actually before this talk, I emailed Sebastian and I wanted to get his model working and I didn't have time to do it. But he's come up with a sort of simplified version of a non-local sediment transport that also, so the top equation, the change in elevation with time, is equal to entrainment function and a deposition, and the deposition depends on a kind of length scale of transport. So this is sort of a simplified version of that non-local model, which tends to look, it behaves quite a bit like the nonlinear model I've talked about before. So this might be one of the ways that we could start to test on a more broader landscape scale these non-local models. Okay, then there's this other series of papers that have recently come out. Again, very exciting. So there's two ways of looking at the actual physics of granular interactions. So there was so the paper on the left coming out of Israel, where you've got a discrete element model. So the actual physical interactions between real particles, well, not computational particles with real physics. And then out of the University of Pennsylvania, you had another series of these sorts of experiments. They say kind of, well, maybe the authors of those papers are listening to this talk. They say slightly different things, and I haven't quite wrapped my head around the implications of that. So in this Ferdowsi paper, actually, I'll go back. What you have is a transition. So they did not disturb this pile of particles. They just tilted it. And what you got is a creep-like motion where you had, the whole thing was kind of creeping. And then if you tilted it up, you got a transition to a more flow-like behavior. Okay, so there's these two different behaviors that the model is predicting. Once you get that fast motion, it tends to concentrate more near the surface. In the Ben-Dror and Gorin paper, you ended up getting, as you tilted the surface more, you ended up getting more of the depth of the particles activated. So again, I think I haven't completely come to terms with these models, but this is very interesting. Simulating this stuff takes a long time. You need a supercomputer, and you end up with a tiny hill slope. So transitioning this to a real prediction of topography is very difficult. In the PNAS paper on the right, they actually tried to come up with a flux law. I thought this was really exciting. They're calling it a glassy flux law because it shares some of the same features of the physics of glass. And there was a test on 2 different hill slopes. I feel like this could be tested on a wider array of situations. I think that's a pretty exciting development. And finally, there's this really cool work that is, they use diffusing wave spectroscopy. So the preprint you can see there at the lower right. They're shining a laser through a pile of grains, which allows you to see small changes in the forces and displacement on the order of 10 to the -6 meters. So you actually have a chance of seeing what the grains are doing. The outcome of this is that things, if you just disturb it and let it relax, you get these granular motions for many, many days after you've disturbed it. And if you do things like if you tap the pile of sediment, you end up with this layer of kind of consistently moving particles. These experiments, going back to the roaring experiments all the way back in '99, so that had a quite innovative way to disturb their sand pile. They used a sand pile. It had acoustic noise to disturb it, which you can argue about how appropriate that is for a real landscape. So I think the evolution of this is trying to get at different particle sizes, different disturbance mechanisms. So actually the left here is a thermal disturbance, on the right is this tapping, and you get quite different behavior with the two. But I think these experiments have a lot of potential to go back and inform what our sediment flux laws are doing. But if we go back, so I said in the abstract, well, we didn't know anything. I don't know anything. I retract that statement. It got you to this talk, but I think the nonlinear model does pretty well, but it leaves a lot of kind of tickling sensations in the back of your brain that are addressed by these new approaches, the non-local approach and this kind of discrete element model type approach. I think the latter of which could come up with some new, and already has, some new flux laws. What are we going to do once we get those flux laws? Well, I think the key thing from a large-scale geomorphic point of view, and what I would be interested in looking at is, well, what are the implications? So the non-local, for example, gives you very similar topographic outcomes to the nonlinear and the non-local have similar topographic outcomes, but I think the transient behavior is going to be the interesting thing to test. So can we actually, if you change your uplift or any other forcings of your landscape, are you going to get a different time series of behavior? So what was this talk about? First of all, the nonlinear model we have is pretty difficult to falsify, so it gives me a little bit of confidence. So maybe I do know a little bit about hill slopes, but it has really unsatisfying parameters. There are alternatives that are being developed, and other people are doing that. Maybe I can contribute to that later in my group, but I think what's happening in the field is really super exciting right now. It's a fun place to be. But those alternatives aren't tested very much now against real topographies. That's to come. Another thing is that the talk is not as good as the abstract, and I really spent a lot of time thinking about the font choice for my cat, which is shown here. So with that, I have gone 1 minute over the hour. I apologize for that, but I will take any questions. Thanks for listening. I'll stop sharing my screen as well.
Thank you so much, Simon, for an excellent talk. And I welcome everybody now to join us in the discussion, and you can post comments or questions in the chat, or you can raise your hand. And we also have Charlie and Philippe that will help out organizing this discussion.
I'm delighted that people are still here.
And I see we already have a few questions. I don't know, Philippe and Charlie, do we have an overview of the order we should go in now?
Yeah, sure. Well, we can go ahead, and it looks like one person has their hand up. So why don't, Jesse, you go ahead and unmute yourself if you want and ask a question, and then we'll go to the chat. Or do we have to unmute?
Yeah, thanks. I was trying to see how I could visually communicate this, but there you go, you found that. So Simon, thanks for a great talk. I must admit that the last 15 minutes went straight over my head. It seems very complicated. But I think the first 40 minutes or so, you really kind of started getting me thinking about, taking 2 steps back. So you said, okay, we want to have laws so we can upscale, over entire landscapes. And so I'm going to kind of try to challenge you here in terms of the approach that you're kind of pushing. So this is just a yes or no question. It's not my real question. And it is, you are saying that relief, that hilltop curvature is a better measure or proxy of erosion rate than relief. Is that right?
Yes.
Yes, exactly. Okay. And so you've showed very nicely how you can do that, and I'm very impressed with that. And so there are many global compilations, or, there are global compilations of erosion rate, that may be used in other applications as well. But, a way to do that is to use the relief. And, if you're doing it at a global scale, you maybe take 5 kilometer resolution relief, right? And you can kind of say, okay, we're using this as a proxy for erosion rates. Now, how would you do that with curvature, hilltop curvature? Is that possible? Do you believe that we can do that?
I do, but you need very high resolution data. So, so Stuart had a paper where he was looking at, could we recover things like the channels and the curvature from lower resolution data. If you've got 30-meter topographic data, it's totally useless. can't see that. You can't see the curvature at all. You can't extract the right channel network. It's useless. You can't do anything with it. Once you get to 10 meters, you're getting there. The problem is, like, if you're getting discrete topography, you're filtering the data, really. So you lose the lower the resolution, you lose the high amplitude features of the landscape. So if you're going to places that are steep and you've got 10-meter data, it's going to be a real challenge to extract the ridgetop curvature. I mean, so with that paper that Manny's leading, we're using 1 meter data. I think that you kind of want to use something on your 1 meter. You might downscale that to sort of 3 meters or so. Again, Stuart said that you could kind of get decent curvature in low relief landscapes with 10-meter data. Once you get to the sharp mountain ridges, I mean, just if you're walking along a ridge and it's not 10 meters wide, if the sharp bit's not 10 meters wide, you're not going to pick it up in curvature. So basically, what we need is a higher resolution global map of topography.
And quantum computers.
Yeah, well, I don't know. I mean, so the hillslope code is slow, but I don't think that's beyond our. So I think we could computationally get all the ridgetops and the curvatures out. I think we could do that. It would take a while, but with our current computational resources, we could do that. What we don't have is our global LiDAR DEM. That's what we don't have. So I think that's the barrier.
Okay, thanks, Simon.
Okay, we have a question by Odin Marc. So he thank you for this very good talk. He asked, on the slide about transients, you show a river nick point propagating and the hill slope responding after it. What would be the story for the Feather River, where you assume that the hill slope have responded faster than the channels?
Well, so if you've got the hill slopes responding slower than the channel, then there's a lag between the ridgetop response and the incision of the channel, which would push the E star R star point north up, right? So anytime you've got that lag, you end up with higher relief for the same curvature. So it would just drag all the points up, and you start to not believe it. I mean, I think that the response time scale of hill slopes, I always sort of assumed that the response time scale of hill slopes was really long compared to the channels. And I think there's a lot of people who still cite the Fernandez and Dietrich paper where they went through the time scales of response to the linear flux law, which is slow. It's very slow. When you have the nonlinear model and you've got slopes near or very steep slopes going to the river, the response time scale's very short. So if the nick points are migrating slowly, then the ridgetops are equilibrated to what's happening in the channel. And actually, the Bolinas paper, we for many years I've been trying to find, so the nick points move up through the landscape, there's a delay, and the ridgetops respond. I've been trying to plot that in space, like up a channel, and that's what Martin and collaborators on that paper we were trying to do. We couldn't find that signal in the Bolinas data. So I think, and we also get sort of that same pattern in Sierra Nevada. So I think that you're not getting that lag between the ridgetops and the channels, and so we think we can make this kind of steady state assumption there. But yeah, it does make you kind of nervous when you make that assumption. But I do think that the timescale response is short on the hill slopes there.
Thank you. So there is also a comment by Odin, but I think we can skip it because you will have access to it through the chat log that we will give you after that.
Okay.
Great. So the next question is from Monica Rasmussen. I apologize, Monica. We have questions pouring in, so I'm just going to choose one of these, and then if we have time at the end, we can circle back. So I'll go for question 2 here, which is that do you think that lithology should be included in the critical slope parameter as opposed to the sediment transport coefficient, and that bedrock stress history, so things like joint orientation, could explain some of the variations that you are observing in that critical slope parameter?
Yeah, Well, this has been a topic of, so not for the critical slope, but for the sediment transport coefficient, about what does lithology do? And I think this falls into the same category of types of questions. So Manny and I have been discussing that a lot, and John has been arguing with us a lot about this as well. But I mean, so on the one hand, the fracturing thing conditions the slope, but we're kind of assuming that the motion of the soil is in the friable regolith layer, right? The mobile layer. So once it's detached, I mean, unless it's a particle size driver, then I'm not sure what the bedrock's going to do, unless the topography of the slope is controlled by the bedrock and not the actual sediment transport, which is a whole totally new can of worms that we would have to open. So yeah, I mean, there are slopes that you can look at in LiDAR in Tennessee, where I used to live, where there's layered sediment, and you end up with like steps in the landscape which seem to be correlated with this layered sediment. And it's not clear to me how what is happening in the bedrock is actually, because once you form soil, you know, it's a soil production thing and not a sediment transport thing that's leading to those steps. So I'm quite confused by that. But yeah, I think if the fracture network is involved in the critical slope or the sediment transport coefficient, it's going to most likely be through a particle size mechanism that we don't have a very good handle on. Yeah, and the other thing about constraining the critical slope, like all of the stuff that constrains things with the fracture network, is that it's very hard to quantify the fracture network. I mean, Roman did a great job of explaining how he does that, but that's a massive challenge. Hopefully that wasn't too waffly an answer. I fear all my answers are going to be waffly, but there you go.
Okay, I can read out the next question for you. So that's from Kai Deng. Thank you for a very informative talk. I have a question on curvature. Why does curvature work better to predict erosion rates at steep slopes compared to relief? Is there a geomorphic mechanism behind it, such as a linear law between curvature and stochastic erosion processes?
Yeah, I mean, this is just that when you get fast erosion rates, the side slopes reach this critical angle. They can't steepen up. So it doesn't matter how fast you're eroding, the side slopes aren't going to get any steeper. They're stuck at that. So the only wiggle room you have is at the ridge. That's assuming you still got a bit of soil on the ridge. But when we do this, we run some metrics to try and see if there's too much rock at the ridge. But that's really it. The relief is just limited by this critical slope angle of the ridges. And once you hit the critical slope angle, you can't steepen the side slopes, but you can still get sharper and sharper ridges. And we've been able to see that in the data.
We have a question by John Armitage. He just went on the field and saw some evidence of runoff eroding the hills. And he asked, is it normal to ignore surface water erosion when studying hill slopes?
Yeah, so this might be what's happening at the toe of our slopes. You know, we're not putting a surface runoff component into this. So in the Sierra Nevada, for example, we went there after a burn. It had burned. There was zero evidence of surface runoff. I think in a lot of these forested catchments, the infiltration capacity is super high. So you basically never get surface runoff. Yeah, so I mean, it's a good point. There are probably places where we're missing that toe slope surface runoff, you know, some kind of you know, water-driven transport at the toe of the slope. But I think in a lot of our forested catchments, that problem is fairly minimal. I also think, you know, like in the Appalachians as well, I've not seen runoff. So in your landscapes, that might be different, but yeah. So it's basically an infiltration capacity question, I think.
Great, thank you. The next question is from Rachel Bosch, who's asking, using the DEM approach, do you think it would be reasonable to try to strike a balance between the computational expense and the physics by using a lower resolution, basically, I suppose, fewer particles or larger particle packages to model hill slopes at a larger scale?
Yeah, well, I'm not really qualified to answer that, I think. I mean, well, there's two versions of these particle models. One is a more mechanistic type thing, like the thing that various people have done to, what Seb's done, and I think, Charlie, you also have papers like this. So you've got individual particles that you're tracking through a hill slope where you can have a reasonable number of particles. But then you also, this other approach, which is like a real you're modeling the physical interactions between individual particles. And again, I'm not an expert on that, but I think like if you brought that before physicists and you said, hey, can we take out the particles? They'd say, no way, because you're gonna miss out the interactions. So I think what Bruce has done in that PNAS paper is the right way to go, which is to try and take really detailed models and then scale it to a flux law. I think that's probably the most likely way to translate those. I don't think a reduced complexity discrete element model is going to really work. But again, I think probably people who have written those papers might be here. I'm not going to scroll through everyone who's watching this talk, but the Landscapes Live team should invite them. Actually, Liren already talked about this in one of her lectures, but yeah, it's a super interesting approach, but very computationally heavy and difficult to scale up to a landscape scale.
Great. So this might be the time. One of those folks has their hand up. So it looks like Doug Gerelmack is here and has his hand up. So maybe he wants to.
I'm glad Doug's going to correct it and say everything I said was wrong. So that's brilliant. Go for it.
Oh, hi. No. That was great. No, I don't want to waste too much time. Just to make a clear point, and then Rachel, you can follow up, or anyone else that's interested can follow up later, is that the fundamental thing is that the way to think about coarse graining a discrete element method model is like coarse graining turbulence in fluid, right? So you know that when you have a turbulent flow, that you create a lot of other length scales. The mixing isn't occurring molecule to molecule anymore, right? You have coherent packages. Similarly, when you have grains creeping, you get these force chains. So you introduce this complex network that makes other scales in the problem. But it's not really just one scale. So it's somewhat akin to like turbulence, where we know that the emerging scales of these contact networks create new scales of mixing and force transmission, but it's non-trivial how to coarse grain it. So if you just made your blocks bigger, you'd really mess up the problem, right? Because you then just introduce connections among them that could be at the scale of your landscape, which isn't what you want. So you need to think of a clever way to essentially deal with the larger length scales and the stress transmission that comes from them. And one of the most promising ways to do it is these elastoplastic models that people are developing in glassy materials, where it's very similar behavior. And of course, you can't really simulate molecules interacting with each other in a glass. So people are trying to come up with essentially, they are kind of rules for interaction at scales much larger than molecules, but much smaller than the material, that appropriately encapsulate these kinds of relaxations and rearrangements. But it's not an obvious answer. It's a very active field, but you have to be careful, just like in turbulence, you have to be careful.
Great,
thank you
so
for
much,
that intervention, Doug. I'm glad someone who knows what they're talking about can comment on those last few slides.
Okay, we have another question from James Kirchner. Super talk, he says, I'm intrigued by the statement that these new alternatives to the nonlinear model have better physics. IRC from a while ago, the glassy transport law predicts finite transport rates on completely flat surfaces. How is that supposed to work? The physics is fancier, sure, but how exactly does it map onto the real world, where, for example, cohesion is important but missing in the glassy model?
Yeah, well, this Q&A could become a conversation between Doug and Jim, but I mean, I do. So in the glassy model, it's hard to get at what's happening at the ridge top. So what I'm basically not going to answer this question because I don't, you know, it's not my paper. But what I would like to see from the authors of those papers are more of this family of tests against real topography. So, you know, looking at, well, do the ridges sharpen? What's happening near the divide? Because that a lot of the interesting behavior. So those the Doan et al. Papers, they were seeing like the discrimination between the non-local and the non-linear. A lot of the action was happening close to the divide. So I think again, I'm kind of obsessed with hilltops, but so I won't really answer Jim's question. And Doug could probably like ring him and talk to him for a few hours about that. But yeah, I think any of these laws, you know, once you do it and you start to get a little bit of confidence in it, you just need to keep exposing that law to stress, which is testing it against topography. So, you know, I think that could the DEM based models and the non-local models could use more pushing against real topography than the nonlinear model, which has sustained a lot of testing. So yeah, I still feel okay using that nonlinear model, despite what I said in my abstract.
Okay, we have a question by Michael Kirby. Your model seems to be transport limited. For nonlinear models, movement become more supply limited. So what happens on slope that are, and also what happens on slope that are steeper than the critical slope?
Yeah, so well, this is what I was saying about it makes you queasy, the model. So what happens on slopes, you can't, if you're doing the model simulation, you can't simulate anything on slopes greater than the critical. And again, I'm like in those numerical models, well, I should say what we're doing when we test against topography, we're using a one-dimensional prediction without, there's no bedrock and sand layer in it, or surface topography layer. So we're assuming the whole thing's a pile of sand. So, you know, think of that what you will. So we're not trying to, it's not, what we're doing is not a landscape evolution model like, say, Josh tried in that 2008 paper. We're just making a prediction based on a one-dimensional outcome of that flux law, and then comparing it to real topography. When I, you know, again, that critical slope makes me uncomfortable. I mean, I think the slide I showed with Sebastian's model, the Cedra model. So there's it's got an entrainment and deposition. And in that model, there's still an S sub C parameter. There's still critical slope, but all the critical slope does in that model is it lets the sediment just move infinitely. So it goes out of the system immediately. So it's a little bit more physically intuitive than an S sub C that we kind of need to tune. And then you end up with places where you've tuned the S sub C and then your real landscape has stuff that's steeper than that. So it's makes me slightly uncomfortable. So yeah, hopefully that answers the question.
All right, they keep coming in. So this is a question from Tyler Duan. Thank you, Simon, for a great talk. Do you have thoughts about what the ideal scale to measure curvature would be? If you had a continuous signal of topography, what scale would you choose?
Well, I don't know if this is a trick question and you're going to tell me that the spectral signature is, you know, important at like micron scale, but you can type in if it's a trick question. But I mean, we're kind of pragmatic. Like if you see the ridge is curving over and you can, you know, so if it's gone linear 1 meter away from the divide, well, you need probably a higher than 1 meter resolution DEM. So at Dragon's Back, we actually I think we had a high resolution point cloud. I think we went to 0.5 or maybe 0.25 meters for the raster of that. Usually, I think, except in extreme cases, like if you've got, I don't know, some marl bedrock and you've got super sharp ridges, usually 1 meter is probably going to be okay. Again, we've done some of this, sensitivity of this, and it depends on the wavelength of the ridge, is the kind of, again, waffly answer. That's all I'm capable of giving. But I think in most landscapes, if you balance like computational expense and the actual sharpness of the ridges, 1 to 3 meters is probably gonna do it if you're trying to compute a whole landscape. Hopefully that is a reasonable answer.
Yes, thank you. I think we have lost Charlie, but it's okay. We have a question by Riza Madoff. On shorter timescales, climate may have a larger impact on erosion in certain regions. Do you foresee a need for developing different landscape evolution model for different regions?
Well, yes. I mean, the process regimes can change. I mean, we've focused on these upland, potentially forested landscapes with high infiltration rates. So we think that there's not really surface runoff. We try to stay away from places that have big deep-seated landslides. So you're not always going to get the conditions that are amenable to this approach, but I do think what we're trying to do works across a pretty broad swath of the landscape. I mean, I did, so Switzerland just released all of its LiDAR data, and if you scan through the landscapes of Switzerland, and you think, is this model going to work? You don't have your nice rolling hills there, or maybe in very limited places. But so I think the landscape evolution model needs to be driven by the processes that you can see in the landscape. But if you've got your sort of slightly linear side slopes, your nice curvy ridge tops, not an overwhelming amount of bedrock, you've got a soil mantle, and you've got reasonably high infiltration capacity, I think this does okay.
All right. We have another question from Anne Voigtlander. Hi, Simon. Thanks for the nice talk. I also feel very about the threshold hill slopes or critical slopes, but it's not necessarily how we try to quantify them, but rather the assumption it's based on that the slopes are critical or at a threshold. Does the slopes represent the critical state? This assumption would need to be tested first, or ?
Yeah, I mean, so back to the original model, the critical slope was based on the material properties, and then it was tested against this physical model in the laboratory. So I think that was a fairly rigorous test of that. But then, of course, when we try to trot it out across entire landscapes, we're really just looking at the empirical evidence. If you don't get any slopes steeper than that, we're fitting, we're curve fitting, really. So it's not like we've gone out and tried to dig a hole and see if the whole hill slope falls into the river. So I guess in that sense, we're not really testing whether or not the hill slope is critical. We're basically fitting this parameter to observe topography. So again, point taken, but we're trying to be kind of pragmatic about how we approach that problem.
Okay, I think we have 1 or 2 questions left. We have one by Kiaran Arman. I'm sorry if I don't pronounce it correctly. Okay, but what is that curvature versus squares of erosion rate relationship about?
Yeah, well, you can read the paper when it comes out. I'm talking about this at EGU. It's Manny and I have had so many arguments about this. I mean, it's like you would have never expected that trend to emerge. We've had loads of arguments about it. You know, it's like, oh, is that a soil thickness thing? I don't see how soil thickness works, because in the depth-dependent transport models, the thicker the soil, the faster the transport. You know, the more space you have to move material. But in faster eroding landscapes, you have thinner soils. So basically, it's the opposite of what you need. We've explored the particle size thing. So there was a paper by David Furbish who was showing the particle size, potential particle size dependence on the sediment transport coefficient. So that works in the right direction, because, you know, our group and others have looked at particle size changes with different erosion rates, and it's moving in the right direction. However, I mean, those landscapes are scattered all over the United States. So it's like, well, it might be all crystalline rock, but the particle size distribution can't really be the same between those places. And then we also explored a kind of fracturing thing. You know, we had conversations with various people, but you know, it's hard to constrain the fracturing. The topographic stress thing doesn't seem to work for us, although John's arguing with us about that. But I just, like, our explanations are kind of failing to come up with a good explanation of that, which makes us suspect we've basically got the rules wrong. So I don't. Well, you can read the paper that one day might come out. There's a preprint on there, and if you're interested, I can email you the preprint. But yeah, we don't quite know what's going on, and Manny's not going to jump in and say anything either, because he's maybe thinks that I've made a fool of myself now.
Thank you, Simon. So there is quite a very enthusiastic discussion about Doug paper and other facts. So you can read it later on. There is, I think, one remaining question by Jen Willenbring. It seems like you are using river erosion rates. Is it correct? And so how do point soil erosion data compare?
Point soil data. I'm wary of point soil data, because, like, if a tree fell over 400 years ago, you're going to get a very weird point soil data erosion rate. So, I mean, we've not tried. So we do have point soil data from the Feather River. There's a few other places, but because it's so local, I think it's more prone to noise. I think I'm more comfortable with the averaging nature of the basin-wide erosion rate. I mean, again, it does depend on, like, well, no landslide in the catchment and that sort of thing. So you might argue it's just as variable as the soil pit. But the other reason is because it's easier. So that's another reason. Like, lots of people collect that data. When you go and collect, there's a lot less or far fewer soil pit erosion rates out there, just because, you know, usually that gets done to do soil production rates. So you need, like, a vast amount of money to get one soil production rate. You need many samples, so you just don't get the same spread of samples. So so again, that's my kind of pragmatic, slightly unsatisfying answer to your question.
Thank you.
Thank you. So perhaps one final question that just came in from Jason Dodge. Nice talk, really interesting concepts, and I look forward to giving this a try at some point in Kentucky. From what you said, I assume our 1.5 meter liter derived DEM should be sufficient for our low but sharp ridged hills.
Yeah, Jason, it's great to hear from you. Riverside people need to stick together. So in Kentucky, I would say the ridge tops are definitely smooth enough to use a 1.5 meter DEM. I think you could probably even downscale that to speed things up. So I mean, in the kind of karstic bits, you might, well, I probably wouldn't try this in the karstic bits, but I think in the, you know, like on the Allegheny Plateau and other places where you've got sedimentary or sandy stone type stuff, the 1.5 meter will work great.
Great. So I think we will wrap it up here. Thank you again so much, Simon, for giving this great talk. And your computer stayed.
Yeah, it stayed up.
the whole time.
Well, I'm a little disappointed because everyone was waiting for your routine, your Danish routine.
Yeah, well, actually,
We'll get that in the next series.
I'm the kind of person that doesn't know a single joke, so I'm very happy that it didn't come to that. Yeah, good. But I think we'll close the meeting now, and we'll make sure to send you the chat so you can read up on all the different comments that came in.
Okay, thanks. I just want to say to Dimitri, with this question, when you're doing fonts for a talk, you really need to go deeper than Comic Sans. It's a cliche. So you've got to explore the Microsoft font family. Yeah, so I think that's a really key part of making a talk. Thanks for the question.
All right. Thank you all for coming and joining us today, and for the great questions that you had. And see you again in May when we have a new lineup for the spring series.
Okay, thanks for listening, everyone. Yeah, bye.